This is video number 2 for sections 6.4, 6.5, and 6.6, factoring binomials. We're continuing through our overall factoring strategy. We saw last time step 1, pull out the GCF. That's always where you begin. Well, step 2, after you pull out the GCF, is to count how many terms you have left. That is a critical step because there are different methods based on the number of terms you're looking at. So you're going to want to learn to count those terms. This video will cover the situation where there are 2 terms, in other words, where you have a binomial. It turns out that for binomials, there are very few ways you can actually factor them. Most binomials cannot be factored. In fact, there are only 3 categories of problems where you can actually do the factoring. The first category is what's called a difference of squares. And this one relates to something that we talked about in the last lesson. Take a look at this first example here. You're being asked to multiply x plus 5 times x minus 5. You might remember we were talking about foiling, and we noticed that if your FOIL problem fit this a plus b, a minus b pattern, then something particular happened, namely the middle part of the FOIL dropped out. I would have x times x, x squared. The outer would be minus 5x, the inner plus 5x, the last minus 25, and of course when I go to combine my like terms, the minus 5x and the plus 5x zero out, and I'm left with the simple answer, x squared minus 25. Well, x squared minus 25 is a binomial, and so obviously if I was asked to factor it, which is what I'm being asked to do in the next problem, that just means, could you please tell me the original multiplication problem? Well, I know what that is. We just worked it out. The original multiplication problem would be the x plus 5, x minus 5. The point is simply this. If you, from this point on, see something that fits this pattern, you're going to have to know, oh, that's one of those a plus b, a minus b factoring situations. In other words, you have to know this came from one of those FOIL problems where the OI part of the FOIL, the middle part of the FOIL, went away. This pattern is called a difference of squares. Difference because there's a minus sign in the middle. Squares because each of the 2 terms is a perfect square. X squared is x times x. 25 is 5 times 5. Well, if you ever notice that you have this difference of squares pattern, then the polynomial will always factor according to that a plus b, a minus b multiplication. This is something that you need to commit to memory, that you need to be able to use, and you'll see a lot of this as you go through the homework. Let's work it out in a couple of examples. So here's a fresh example. I'm being asked to factor this polynomial. Step 1, pull out the GCF. Well, I look at my 2 terms. I don't think there's anything in common here. There is no number that goes into both 4 and 81 evenly. The only thing that goes into 4 would be 2 and 4. Those don't go into 81. The second guy doesn't have any x's either. I guess you could say that technically the GCF is a 1, but pulling out a 1 isn't going to do anything, so we don't find that useful. Unless there's a GCF other than 1, we essentially skip that step. So I don't need to pull out the GCF. Step 2, count your terms. Well, I have 2 terms. There are only 3 methods for factoring binomials, items with 2 terms. We've only learned 1 so far. Let's see if this fits our difference of squares pattern. It does have a minus sign in the middle, so that's good. And then I check the first term, and off on the side you could even write down for yourself the a and the b. I'd put it off on the side so it's out of the way of your main work. A just means, is there something that you could multiply by itself to get 4x squared? Sure. 2x. 2x times 2x is 4x squared. Is there something you could multiply to get 81? Of course, 9 times 9 is 81. Well, you've just determined that those two pieces are perfect squares. This is a difference of squares. I don't have to really give any thought as to how this factors. I just follow the factoring formula. It is a plus b, in other words, 2x plus 9, times a minus b, 2x minus 9. That's the answer to the problem. I've come up with the original multiplication problem, in this case a FOIL problem, that makes this answer. Remember, if you're in doubt, you can just multiply it out to check it. Let's take a look at the second example. Factor 3x squared y minus 12y. Again, step 1, pull out the GCF. I think I've got one this time. It looks like I have a 3 as far as the numbers that are in common to both. No x's. The second guy doesn't have any x's, but each one has a y. I can pull that out. Let me open my parentheses. What's left from the first term? Well, I took the 3 and the y, so I still have the x squared. From the second term, I'm clearly going to have a minus, and I believe just a 4. Again, you could always distribute this in your mind to make sure you've done it correctly. Well, I'm not done though in this problem, because after you pull out the GCF, you count up the terms that are left. I have 2 terms left. Of course, that'll just match however many terms you had at the beginning. If there are 2 terms, I need to see if I can keep going. Well, does this fit our difference of squares pattern? I see a minus sign in the middle. That's good. And I am now checking to see if I have 2 perfect squares. Well, it should be pretty obvious. The a would be x. X times x makes x squared. The b would be 2, because 2 times 2 makes 4. Well, I have a difference of squares, so that parentheses keeps going. I can factor further into the a plus b, a minus b pattern. X plus 2, x minus 2. Don't forget the 3y, that's part of the answer. Your final answer needs to be all the pieces you would multiply together in order to end up with the original polynomial. If you were to FOIL these 2 pieces out and then distribute the 3y, you would in fact end up with this polynomial. Let's go on to the second category of factoring binomials. It is called a sum of cubes. And hopefully the name is kind of obvious. This just means I've got a plus now in the middle for the word sum, and instead of having perfect squares, I have perfect cubes. Well, let me write down the factoring formula for you. This one's a little bit more complicated than the other one. If you have a sum of cubes pattern, here's how it factors. There's a binomial and a trinomial. A plus b times a squared minus ab plus b squared. Now you may feel like I just pulled this out of thin air. In order for me to prove to you, to convince you that this is really true, all I really need to do is carry out the multiplication here on the right side and show you that yes, in fact, you do end up with a cubed plus b cubed. Since this looks to be somewhat of a mess, why don't we set it up using a box? I need 2 rows and 3 columns since I'm multiplying a binomial times a trinomial. Let's go ahead and list our terms along the sides. Don't forget the term with the AB has a minus sign that needs to be included here. And now we have 6 multiplications to work out. Why don't you go ahead and try that yourself and then check against my answers. So hopefully this is what you got. Now I just need to combine my like terms. Remember in the box they typically show up diagonally. I believe these guys are like terms and these guys are like terms. But interestingly, look at what happens. I have a squared b minus a squared b, gone. I have ab squared minus ab squared, gone. The only thing I have left here is a cubed plus b cubed. Well, that's what we set out to prove. Clearly, if you multiply this binomial and this trinomial, you get a cubed plus b cubed, which means if you want to go the other way around, this factoring formula will work. Well, let me write down the third category for you, and then we'll work an example. The third category is very, very similar to the sum of cubes. It is called the difference of cubes. The only thing different in the pattern is, of course, I have a minus sign in the middle instead of a plus. The factoring formula is very, very similar. There is a binomial and a trinomial. And in fact, they are very, very similar to the ones we had earlier. The only difference is the minus sign has shifted locations. The minus sign is now in the binomial instead of in the trinomial. If I wanted to, I could do that same proof with the box and show this to you. It essentially just works out the same. You can try it yourself if you want to. But what I would like to do is work an example now. Let's take a look at this example here. We're being asked to factor 27x cubed minus 8. Let's run through our steps. Step 1, pull out the GCF. I don't think I have anything in common. Nothing goes into both 8 and 27 evenly other than 1, so I can't pull out the GCF. Step 2, count the number of terms left. Well, I have 2 terms. Then I just need to see if it fits one of those 3 patterns. It does have a minus sign in the middle, so that'll be one of the differences. And then I'm just wondering, are these guys here perfect squares or perfect cubes? Of course, if they're neither, then I won't be able to do anything. Well, I believe that what I'm looking at is a couple of perfect cubes. That just means I think I can write something down that if I multiply 3 of them together, I get each item. For example, my A, I believe, is 3x, because 3x times 3x times 3x makes 27x cubed. My B would be 2, because 2 times 2 times 2 would be 8. You can, of course, use your calculator to help you if the numbers get excessively large. Now, here's the great thing. We've just realized, hey, it fits this pattern, this one right here, the difference of cubes. Minus sign in the middle, 2 perfect cubes on either side. Well, there's not really much work to be done at this point. You just need to fill in to this factoring formula. So in order to factor this guy, I'm going to have a binomial. In the binomial, I write a minus b. Well, my a is 3x, my b is 2. Then I open up a trinomial. And let's see, the first thing I'm supposed to do is square the a. That means multiply the a by itself. 3x times 3x, what's that? 9x squared. Then I'm supposed to multiply the a times the b. 3x times 2, 6x. Then I'm supposed to square the b. 2 times 2 is 4. That's it. There's nothing left to do. It is a long formula, but plugging into it is as simple as filling in those pieces as we just did. Let me put your mind at ease by pointing out this note here. You don't have to memorize the formulas for sum and difference of cubes. They're kind of messy. I'll provide those for you on the test. You just need to worry about using them. Well, to wrap up, we have one last issue to consider. You might be wondering, what about sum of squares? Why isn't that one of the situations? For example, what if somebody asked me to factor this, x squared plus 4? It's got a plus in the middle. These two guys are clearly perfect squares. Why don't we have a formula for those? And the answer is very simply, there isn't one. It just doesn't exist. You can sit here all day trying to come up with a multiplication problem that makes x squared plus 4. It cannot be done. Some people might say, well, wouldn't it just be x plus 2 times x plus 2? And the answer is no, absolutely not. If you multiply that out, you have an extra term in the middle. It didn't work. There simply is no way to factor this guy. When that happens, when there's no GCF and there's no way to factor this thing at all, we say the answer is prime. That simply means I have no way to give you an original multiplication problem. Remember, there are only 3 categories of binomials that can be factored. Difference of squares, you need to memorize that formula. Sum and difference of cubes, I will provide those formulas. But that's it. All other cases, you cannot factor a binomial.